Welcome back. Let's continue our journey through chapter of 12. So let's do 12C. So continuing with the properties due to an intermolecular interaction, let's see this problem. Which compound would you expect to have greater surface tension, acetone or water? So once more, surface tension is the molecules on the surface are being attracted by the intermolecular forces. The stronger those forces are, the harder it will be for something to break through. So let's analyze the different forces for these two. So first thing, let's go ahead and draw the Lewis structure for acetone. You're gonna end up with something like this. If you still have problem coming up with Lewis structures, come see me at the office or the Science Learning Center. So after you do the Lewis structure, you're gonna notice that this is trigonal planar using the best part table. Then we're gonna analyze the different bonds to see their polarity and see how their polarity comes together to determine if the molecule is polar or not. So this is 3.5, 2.5. The difference is 0.5, which makes it a polar covalent bond. Therefore, we can do a vector force, which is going to make this partially negative, partially positive. This is carbon to carbon, so that's a non-polar bond, so there's no vectors in there. So this molecule is a polar molecule, which means it will have dispersion because it's a polar molecule, which is a dipole. It's going to have dipole interaction with other molecules. And does it have hydrogen bonding? Well, for hydrogen bonding, you need FH present or OH or NH has to be present for hydrogen bonding to be possible. That doesn't happen here. So there's no hydrogen bonding. It's not ionic. So there's two forces going on for this one. What about water? The Lewis structure for water is going to produce, after analysis with Vesper, a bent molecule. Polarity of the bond is going to give us a polar covalent bond here and another polar covalent bond there. When we analyze these two forces, they combine to give us a force like that, which means that's going to be partially negative, and the bottom part is partially positive. What this tells us is that this molecule is a dipole. So therefore, you're definitely going to have dispersion. You're going to have dipole, and you're going to have two places where you can do hydrogen bonding. And it's not ionic, so got two forces versus three forces. This one should have the higher surface tension, and this one will have the lower surface tension. So once more, an analysis of the properties of the molecule tell us which molecule to molecule or intermolecular force should be present. Everything has dispersions. To be a dipole, you have to be polar. And then if you have HF, HO, or HN, then the molecule can also do hydrogen bonding. So this is your daily work. Three answers for each pair. So continuing with another problem, pick the one with the highest viscosity. Remember, viscosity is the property in which molecules can slide past another. They can flow through it. The stronger the intermolecular forces, the harder it's going to be for those molecules to slide by because they're going to be captured, which means higher viscosity. Stronger forces, higher viscosity, but make sure you're able to explain why. So pick the one with the highest viscosity. And we have this molecule, which we're going to call pentane, given that it has 5 carbons. And the other one is going to be hexane, given that it has 6 carbons. And we will talk more about naming organic compounds further into the course. So just so we have a pretty good idea, you will have carbon, hydrogen, carbon, hydrogen, hydrogen. That's what this CH3 means. And that's going to be attached to a carbon with 2 hydrogens. That's what the CH2 means. Attached to another carbon with 2 hydrogens. Another carbon with 2 hydrogens. And a final 5th carbon with 3 hydrogens. We're going to analyze every single bond, but most of them are the same. So this is 2.1 and this is 2.5. The difference is 0.4, which is a non-polar covalent bond, which means the electrons are evenly distributed. So we're not going to get a partially positive, partially negative. And that happens with every carbon-hydrogen bond. The only thing that remains is the carbon-carbon, which is definitely even because you have the same electronegativity on both sides. The difference is 0. So this molecule have no polar bonds at all. It doesn't have any lone pairs. So this molecule has to be non-polar. And if you notice on the other one, it's going to be exactly the same thing. So both molecules are going to be non-polar, which means if the molecule is not a polar molecule, then it's not a dipole. Then it cannot have a dipole-dipole interaction with another molecule, which means it cannot have hydrogen bonding either, because a hydrogen bonding is a special type of dipole. So all this molecule has going for is dispersion. So it's basically dispersion versus dispersion. So how do we know which one had the stronger force? Well, this one have 5 carbons, and each of those carbons have as many hydrogens as possible. And this one have 6 carbons, which means this one is the bigger one. And remember, on dispersion, the bigger the molecule, the more contact you will have with a bigger surface, and therefore the stronger the dispersion force. So the one with the stronger dispersion force is going to be that one, which means it's going to be the one attracting other molecules harder, so it will be harder for them to slide by, which means it's higher viscosity. So this one we have the higher viscosity, this one we have the lower viscosity. Another way you can actually see this one is longer. So they will, with another molecule, they will tend to entangle more, preventing the flowing across each other, which means higher viscosity also. It's like doing pasta and having elbows versus spaghettis, which are longer. spaghettis tend to entangle each other. The elbows do not do that. And here's your daily work. You got two different questions, question 1 and question 2. Find the one with the highest viscosity and explain why. So let's look at an Alex problem to see how this will be presented on a text, for example. So liquid A is known to have a higher viscosity. So A have higher viscosity and a higher vapor pressure. And higher vapor pressure. If you have a higher vapor pressure, that means that a lot of molecules escape and go into the gas and they put pressure on the surface of the liquid. And so if those molecules can escape that easy, that means that it have low intermolecular forces. That's why the molecules can escape. If we have a higher viscosity, that means that the molecules cannot slide past one another. Therefore, the intermolecular forces are high. Do you see a problem with that so far? Yeah, one is telling us that the intermolecular forces are high. The other one is telling us that the intermolecular forces are low. So I would say I don't have any other choice to explain vapor pressure, but I can explain viscosity on a different way. I can say that the size of the molecules is longer, therefore they entangle more and it's harder for them to go past one another. That's how I can eliminate the contradiction on intermolecular forces. So the size is probably the main determining factor. So I'm gonna take this one out of my mind for right now. What about B? Well, B is basically the opposite. So use these facts to predict the result of each experiment in the table below. And the experiment is like this. If I have 25 milliliters of A, so I have, and I always like to visualize it, 25 milliliters of A, which is being poured into a beaker. And 25 milliliters of B, which is also being poured into another beaker. So both of them are being poured into a beaker. After 90 minutes, so time has passed, the volume of A and the volume of B in the liquid are measured. So what would happen? We start with both of them, 90 minutes pass. The volume of A will be greater than the volume on B. Well, we know the viscosity is higher on A, right? So that means it's gonna flow slower. So that would be wrong. We're talking about the volume on the beaker that we're dropping it to. So the viscosity is higher on A, so you're not gonna pour more of A. It's gonna resist flowing through. BA will be less than BB. The volume of A will be less than BB. Yeah, that's the opposite of what we just said on the other one. So that should be right. BA will be equal to BB. No, they're different. It is impossible to predict whether BA or BB will be greater without more information. No, it's not impossible. Basically, what it's telling us, we can answer this without using vapor pressure. just the viscosity, just thinking about viscosity, answer this question. And the question is, the volume on A will be less than the volume on B. Vapor pressure is not a factor on this one. So when you do this type of problems, organize your data like that. What is this telling me about? Do I know the definition of the property first, like viscosity? Do I know how it relates to intermolecular forces? Can I visualize an experiment like this? Can I do a drawing and really see what's going on? And that would be the best way to answer a problem like this. So here's another daily work that you can do based on using the same approach based on what you know about the property that is affecting this. Let's see another problem. Which evaporates more quickly? 55 milliliters of water in a beaker with a diameter of 4.5 or 55, so it's the same, milliliters of water, same substance, in a dish with a diameter of 12 centimeters. So the only thing that is changing is that you have two containers with water, but one, let's call this number 1, let's call this number 2, but one is bigger on diameter than the other one. So, and the question is the vapor pressure of the water different in the two containers? So the vapor pressure is the force that the molecules on the gas state put when they return and hit the surface. Well, let's see that molecules escape from there. So this one have a bigger surface, so more molecules can escape. This one has a smaller surface, so the amount of molecules that can escape is proportional to that phase. And now these ones are putting pressure back there. So at first glance, it looks like the one with more molecules will put more pressure, right? But pressure is based on the particles hitting a surface. Since you have more molecules over here, but the surface is bigger, proportionally, they're going to be the same. So the answer will be no, they are the same. And it doesn't say anything about temperature, so we have to assume that the temperature is the same temperature. So vapor pressure is a physical property. So at a given temperature, the physical property of water, the vapor pressure of water, should be the same, not relative to the amount. It's not an intensive property. So pressure in this case is a ratio between the force that is being put down on the surface by how much surface you have. So in terms of proportion, the proportion is the ratio. The ratio is the same. So if this was 40 degrees Celsius, we don't know what it is. It doesn't matter what, the pressure will be always the same at that temperature. So here's your daily work. And here's another question. And this was on a test a few semesters ago. Which of the following substance will exhibit the lowest vapor pressure? The lowest vapor pressure means that less molecules are able to escape the liquid, so you have less molecules returning and putting pressure into the surface. So for less molecules to be able to escape, that means that there's a stronger force holding them in the liquid. So the intermolecular force, we're looking for the one with the strongest or the higher intermolecular force. So what do we have in here? Well, first thing, let's look at the mass. The mass is basically the same, very close to each other. So I don't think dispersion is gonna be, so we have four forces, right? Dispersion, dipole, dipole, hydrogen bonding, and ionic. So let's do the table. Let's call this, that one is A, B, C, and D. So A, B, C, and D. And the one with more force should be the one with the stronger force, therefore the one with the lowest vapor pressure. So on A, what do we have? This molecule is going to be a polar molecule. So on A, all of them will have dispersion, and we know that they're very similar based on the mass. So the first one is a polar molecule. You can check the electronegativity and so on. So this one we have dipole, dipole. And also you have NH, which is going to give you hydrogen bonding also. So none of them we have ionic. Let's look at the second one. Second one is also polar. So therefore dipole, dipole. Also hydrogen bonding. But notice that there's two places where you can do hydrogen bonding. So I'm gonna say that I have double the hydrogen bonding. When we look at number 3, once more, this is gonna be a polar molecule. So it's gonna have dipole, dipole. It got OH, so therefore it will definitely have a hydrogen bonding. What about D? D have no polarity anywhere, so dispersion only. So D would be the one with the highest vapor pressure because more molecules can escape. So that's not our answer. So which one will have the stronger intermolecular forces? Where all of them have the same 3 forces. However, one of them have double hydrogen bonding. So I would say B would be higher than C, which is going to be higher than A, which is going to be higher than D. And if that is your answer, you get most of the points on this question, but you don't get all the points because you also have to consider that this is 2.1, this is 3.0, so therefore you have something like that. You got priority there. However, this one is 3.5, 2.1, so you basically have a stronger dipole in there. So with the data we have, we don't know is that OH, because of the highest electronegativity, can be more than 2 NH combined. So the best answer would be B equals, I don't know for sure, and C bigger than A, bigger than D. And then you get to explain why you think that there's a question mark between B and C. So you have to consider that. Which one have a stronger dipole? Remember that the super dipole is based on the difference on electronegativity, and 3.5 is bigger than 3.0. So keep that in mind. The difference between these two is 0.9. The difference between these two is 1.4. A little bit less than double the polarity there. So the best scientific answer would be one where you recognize that you do not have enough data to for sure tell me the answer. And with that, we can say that we have covered intermolecular interactions in terms of how they affect physical properties. And we talk about what boiling point is and how it's affected by intermolecular forces. The same thing with vapor pressure, with viscosity and surface tension. And we also discuss capillary action. And you have a daily work where you may have to use capillary action, so keep that in mind. So once more, is there anything of this that you didn't grasp out of this lecture? Now that you heard the lecture, review the textbook, look at the tutorial videos that are posted on Canvas, come to the Science Learning Center, come to my office, email me, whatever you need to do. So take care. See you on the next one, which is going to be part D. So see you soon. Take care.